Welcome to this explainer. Okay, today we're diving into a topic that perfectly blends aesthetic beauty with, well, terrifying structural liability. I'm talking about glass railings. Most of us just look out at a minimalist balcony and enjoy the view. But it turns out, installing these things is this crazy, high-stakes engineering puzzle. As we'll see, seemingly microscopic mistakes don't just cause a minor headache. No, they result in tens of thousands of dollars in absolute demolition. Let's get into it.
Just to put things into perspective, take a margin of error of 5 millimeters. That's what? Barely the width of a pencil eraser, but in this world, it's completely fatal. You see, tempered glass has this unique property where the thermal treatment actually locks in internal stress. So what does that mean for us? It means it literally cannot be cut or shaved down after the fact. If your measurements are off by even a single millimeter, boom. The entire custom pane shatters into useless scrap.
So how exactly does a tiny 5 millimeter mistake snowball into total project demolition? Well, what's really fascinating here is that disastrous structural failures usually start way before anyone even picks up a wrench. It's actually the invisible, early decisions that totally dictate whether a balcony can safely hold a crowd or, spontaneously fail.
To understand how these cascading disasters actually happen, here's our roadmap for this explainer. First, Phase 1, flawed foundations. Then, Phase 2, physics and chemistry. Next up, Phase 3, the final test. And finally, we'll wrap up with the ultimate safety checklist.
All right, let's kick things off with Phase 1, flawed foundations. This is where critical, foundation-level errors happen way before the glass ever arrives on the job site.
Okay, mistake number 1 is a classic clash between theory and reality. It's ordering glass based purely on architectural drawings. Look, perfectly drawn plans almost never match actual human construction. In fact, reality usually brings a difference of 3 to 15 millimeters per bay. And because of that strict 5 millimeter rule we just talked about, yeah, you absolutely have to measure with a digital level and a steel tape only after the substrate is completely installed. You just can't guess here.
Now, here's a term you definitely need to know: monolithic tempered glass. Basically, when this stuff breaks, it shatters completely into tiny fragments and just falls away. Drops right out. The hidden trap here, it's totally financial. Monolithic glass is roughly 30 to 50% cheaper than the safer alternatives. So you can see how it becomes a dangerously tempting substitution for someone looking to, cut a few corners and save some cash.
But compare that to laminated safety glass. With laminated, even if it breaks, there's an inner layer that actually holds all the fragments safely together, keeping the barrier intact. It's a real lifesaver. Using monolithic glass on a commercial project will instantly, and I mean instantly, fail a building inspection. The International Building Code actually requires that retain fragment behavior. If an installer tries to cheat to save money, they're going to trigger an incredibly expensive full system replacement. Total nightmare. And guys, the forces we're dealing with here are just massive. 3,000 pounds. The end posts in these systems, they don't just, hold up a rail. They anchor up to 3,000 pounds of horizontal tension. That is wild. Because of that, you absolutely cannot just blindly pull a standard post out of a catalog and slap it at the end of a run. No way. It has to be independently engineered. Otherwise, it will literally tear right out of its base.
Which actually brings us to our next critical failure point, the substrate itself. Let's say you assume you're drilling into solid concrete. Naturally, you'd use standard expansion anchors, right? But wait, what if you actually have a composite metal deck? Suddenly, your anchor just hits empty air or insulation. Its holding capacity completely plummets, leading to these utterly terrifying anchor pullouts under load. A simple core sample survey beforehand solves all this. It tells you exactly what substrate you're dealing with, so you can use the right solution like toggle bolts or drop-in anchors.
Wrapping up Phase 1, we have mistake number 6, getting the glass thickness wrong. If the glass is even slightly too thin, it creates this really unnerving, kind of bouncy sensation when someone leans against it. And let's be real, you definitely do not want words like flexible or bouncy associated with a 5th floor balcony. Even if that undersized glass somehow passes a quick visual inspection, the second occupants report that the railing moves, you're looking at a complete, highly disruptive replacement.
Okay, let's step into Phase 2, physics and chemistry. This is where we explore how nature, seasonal weather, and invisible chemical reactions secretly attack a flawed installation over time.
So there's actually this invisible physics battle happening right inside the railing, and it's all about the coefficient of thermal expansion. Think about it. An aluminum base shoe expands more than twice as fast as the glass panel when it's baking in the summer sun.
If an installer jams that glass tightly into the metal channel without leaving a tiny 3mm clearance gap, well, that expanding metal acts exactly like a giant vise. It'll just crush and crack the glass as the temperature rises.
Then we have the ticking time bomb of water damage. Imagine this. During a really hurried cleanup, an installer accidentally leaves a small piece of tape over a tiny 6 to 10mm weep hole. Doesn't seem like a big deal, right? Well, rainwater starts to pool inside the base shoe with nowhere to drain. Give it maybe 3 wet seasons, and the glass actually begins to delaminate, while those absolutely critical metal anchors silently corrode away to nothing. All of that destruction just from a careless 5-minute cleanup mistake.
And you know, human nature causes a lot of problems here, too. When tightening the spigot clamps that hold the glass, we instinctively assume that tighter is always better, right? Well, wrong. Actually, if you over-tighten past the specified 20 to 25 foot-pounds, usually because someone isn't using a calibrated torque wrench, you create these extreme stress points in the glass. It causes invisible microfractures. And honestly, the scariest part? The panel might look completely fine when you pack up and walk away, but those fractures secretly grow, causing the glass to just randomly burst weeks later.
Using the wrong sealant is another silent disaster. Acrylic latex loses its grip when wet, and oil-based sealants, they actually attack and degrade rubber EPDM gaskets. But the most surprising culprit is acid cure silicone. If you're working and your sealant has a sharp vinegar smell, watch out. That means it's releasing acetic acid, which will secretly rust your stainless steel hardware from the inside out. You absolutely have to use a neutral cure silicone, no exceptions.
Okay, moving right along to Phase 3, the final test. All that planning and precise engineering finally leads up to this harsh reality check.
Look, the International Building Code doesn't really care if your railing looks pretty. Safety is a rigorously measured structural requirement. During inspection, they will apply a concentrated lateral push of 200 pounds right at the top of the guardrail. If your anchors are weak or your glass is undersized, the whole thing fails. It's a stark reminder that a beautiful railing can still be a deadly one if it can't pass this final physics exam. And believe it or not, it actually gets stricter. While pushing with that 200 pounds of force, the system also has to pass the 4-inch sphere test. What this means is that under intense pressure, the gaps between the glass panels cannot deflect and widen enough to let a 4-inch sphere slip through. Now, why exactly 4 inches? Well, because that's roughly the size of a small child's head. It's an absolutely crucial safety measure to prevent a child from falling through a gap that might momentarily open up just because someone else leaned heavily on the glass.
So, how do we make sure we get it right every single time? Let's transition to our conclusion, the ultimate safety checklist.
It turns out the true hero of a successful glass installation isn't the wrench, it's the clipboard. Pre-installation planning is everything. You have to measure bays after the substrate is installed. You've got to verify you're using laminated glass for commercial guards. Conduct those substrate core samples. Make sure end posts are independently engineered. And of course, verify you have neutral cure silicone. Basically, catching these issues on a clipboard on day 1 is what saves you tens of thousands of dollars in demolition on day 100.
The final sign-off really boils down to a measurable timeline. Minute 1, you check the logs to verify a calibrated torque wrench was actually used. Minute 5, you simply pour a bucket of water into the base shoe to guarantee it actually flows out of the weep holes. Such a simple test, but so effective. At minute 10, you conduct and record that 200-pound lateral load and deflection test. At the end of the day, solid documentation beats visual guessing every single time.
I think this quote brings our explainer home perfectly. It says, "These are not failures of craftsmanship. They are failures of specification and pre-installation verification." It hits the nail on the head. Massive legal liability and randomly shattering panels are completely preventable. It really just requires a healthy respect for physics and a whole lot of meticulous planning. Which leaves us with one final thought. The next time you walk out onto a high-rise balcony, leaning against that seamless, invisible barrier of glass protecting you from the drop, will you just trust the beautiful view? Or will you be thinking about the invisible checklist, the calculated torque, the precise chemical sealants, and the sheer hidden physics beneath your hands that ensures you safely see tomorrow? Thanks for joining me on this explainer, and hey, keep questioning the structures around you.